Ancient engineers built complex machines that predicted modern science. By the end of this journey, you will see history not as a slow march forward, but as a story of brilliant flashes lost to time. How did a 2,000-year-old device compute planetary movements with precision gears? Why did a self-healing concrete formula vanish for centuries? This exploration reveals 25 forgotten inventions that prove our ancestors came startlingly close to our modern world. What does it say about progress when such advanced knowledge can simply disappear? One of the most startling artifacts ever pulled from the sea began as a lump of corroded bronze. Spongedivers working off the coast of a Greek island in 1900 recovered the unassuming mass from an ancient Roman shipwreck, along with beautiful statues and glassware. For decades, this corroded chunk sat in a museum storage room, its true nature completely hidden. It was only when a scientist began examining the fragile layers that the truth started to emerge. This was not a piece of scrap metal. It was a machine, a complex clockwork device of staggering ingenuity, now known as the Antikythera Mechanism. Through painstaking analysis and advanced imaging techniques like CT scanning, researchers have slowly decoded its secrets. The device was a sophisticated astronomical calculator built around 100 years before the Common Era. It housed more than 30 interlocking bronze gears, each meticulously hand-cut and designed to mesh with perfect precision. By turning a hand crank on the side, the user could set the mechanism in motion. Dials and pointers would then whirl into action, predicting the movements of the sun and moon, the phases of our lunar neighbor, and the timing of solar eclipses years in advance. It could even track the cycles of the ancient Olympic Games. Inscriptions on the casing, a sort of ancient user manual, explained the complex celestial dance it represented. Think about that for a moment. This was not a simple model. It was a physical simulation of the cosmos, a miniature, mechanical universe inside a wooden box. The knowledge of astronomy and engineering required to create such a device is breathtaking. It means the ancient Greeks understood celestial mechanics with a precision that historians never thought possible for that era. The most sobering part of this discovery is what followed. Technology of this complexity simply vanished. Nothing like it would appear again until the development of intricate astronomical clocks in Europe, more than 1,000 years later. Its very existence forces us to reconsider the technological ceiling of the ancient world and to ask what other brilliant creations were lost in the fires of libraries or the silence of sunken ships. While the Antikythera Mechanism represented a pinnacle of peaceful calculation, another ancient invention channeled similar ingenuity into a more fearsome purpose. Picture a Byzantine warship confronting an enemy fleet on the open sea. Instead of arrows or rams, a bronze tube mounted on the deck erupts, spewing a torrent of liquid flame that clings to the water's surface and refuses to be extinguished. This was Greek fire, a weapon so potent it could decide the fate of empires. Developed around the year 672, this terrifying substance became the Byzantine Navy's ultimate advantage for centuries. Its very nature defied logic, a fire that water only seemed to feed. Historians believe its secret formula likely involved a base of crude petroleum, enhanced with ingredients like quicklime, which reacts violently with water, generating intense heat and possibly even igniting the mixture on contact. This was not mere alchemy, it was applied chemical engineering. The Byzantines did not just possess the formula, they engineered a delivery system. Specialized bronze pumps and pressurized siphons allowed them to project the fiery stream with devastating accuracy, creating the world's first functional flamethrowers. The psychological impact was as powerful as the physical destruction, creating an aura of invincibility for the empire that held the secret, and that secret was guarded with an obsession that ultimately led to its loss. The knowledge was so compartmentalized, so tightly controlled by the imperial court, that when the Byzantine Empire finally fell, the formula for Greek fire vanished from history with it. Modern scientists and chemists continue to experiment, trying to recreate a substance that ancient engineers perfected over 1,000 years ago. Its legacy is a haunting reminder of how advanced chemical principles could be, and how a single, fiercely protected invention could shape the course of history before disappearing into the shadows of time. That mastery of chemical fire stands in stark contrast to a much quieter, yet equally puzzling, discovery from a different ancient empire. In 1936, a museum expedition unearthed a set of peculiar clay jars near Baghdad. These were not ordinary pots for storage. Each one contained a carefully arranged assembly, a copper cylinder sealed inside with an iron rod suspended at its center. To an untrained eye, they were simply curious relics from the Parthian era, a period spanning from 250 years before the Common Era to 224 of the Common Era. But when researchers began to test their properties, a startling possibility emerged. If you filled one of these jars with an acidic liquid, something as common as vinegar or wine, the chemical reaction between the liquid, the copper, and the iron would generate a small but measurable electric current. These unassuming objects could produce about 1 to 2 volts of electricity. They were, in essence, primitive batteries. The exact purpose of these ancient power cells remains one of history's great debates. Some theories suggest they were used for religious rituals or medical therapies, perhaps to create a tingling sensation. Yet the most compelling evidence points to a practical application that seems pulled from a modern workshop. When connected in a series, these batteries have been experimentally proven to be capable of electroplating. This is the process of using an electric current to deposit a thin, shimmering layer of gold onto the surface of a silver object. Replicas of the Baghdad Battery have successfully accomplished this very task, gifting a common metal with the appearance of a precious one. Consider what this implies. Nearly 2,000 years before Alessandro Volta is credited with inventing the modern battery in 1800, artisans in Mesopotamia may have been harnessing the fundamental principles of electricity for their craft. This was not magic, it was an applied understanding of electrochemistry. The implications are staggering, forcing us to wonder if this was a lone, isolated experiment or a glimpse into a more widespread, but now entirely lost technological practice. How many other simple batteries have crumbled back into the earth, leaving no trace of the small sparks they once created? While the Baghdad Battery offered a fleeting spark of ancient electricity, another Roman innovation provided a form of structural immortality. Marvel at the piers of a 2,000-year-old Roman harbor, their concrete blocks defiantly intact despite constant assault by saltwater waves. Modern concrete, by stark contrast, often shows severe decay after just 50 years in the same harsh marine environment. This incredible durability stems from a deliberate and brilliant recipe. The Romans created a special maritime concrete by mixing lime with volcanic ash, specifically a type of ash from the Pozzuoli region, and then used seawater to bind it all together. This was not a simple mortar, it was a chemically active substance engineered for the long term. When modern scientists analyzed samples with advanced microscopes, they discovered the secret. Seawater filtering through tiny cracks in the concrete actually triggers a remarkable chemical process. It reacts with the volcanic ash to form rare, interlocking crystals that gradually expand, sealing the cracks from the inside out. The material does not merely resist damage, it actively repairs itself. This self-healing property is why the magnificent dome of the Pantheon in Rome, a structure built without any steel reinforcement, still stands as the largest of its kind in the world after nearly 2 millennia. Today, material scientists are racing to decode this ancient formula, hoping to replicate its properties to create more sustainable and resilient modern concrete. This would drastically reduce the environmental cost of constant repairs and rebuilding. The profound irony is that the Roman builders achieved this through generations of practical experimentation, not through a scientific understanding of the molecular chemistry at work. They perfected a technology through observation and results, a solution that in many ways still surpasses our own and quietly anticipated the goals of modern material science. How many other such empirical masterpieces are hidden in the ruins of the ancient world, waiting to teach us their lessons once more? That same Roman concrete which built empires with stone was matched by a Greek mind that mastered the air itself. In the 1st century, the brilliant inventor Heron of Alexandria described a device of breathtaking simplicity and power, the Aeolipile. Picture a sealed bronze sphere, suspended so it could spin freely above a kettle of boiling water. 2 pipes channeled steam up into the sphere, where it escaped through 2 opposing nozzles bent at sharp angles. As the steam shot out from these jets, the sphere itself was sent whirling in the opposite direction, a humming, rotating globe of metal and force. This was not just a curious toy, it was a working demonstration of a fundamental law of physics, the principle that for every action there is an equal and opposite reaction, a concept formally defined by Isaac Newton more than 1600 years later. Heron's device was, in its purest form, the world's first recorded steam turbine. It proved that the ancient Greeks understood how to convert the raw energy of heat into controlled mechanical motion. Heron documented this and other marvels in his book Pneumatica, a volume filled with automated wonders. He designed temple doors that appeared to open by divine magic, powered by heated air and counterweights. He even created what might be the earliest known vending machine, a device that dispensed a measured amount of holy water when a coin was inserted. The Aeolipile stands apart from all these, a spark of pure potential. The ancient world possessed all the necessary components for a steam engine, the boiler, the piston-like action, the rotational force, yet this path was never taken. The Aeolipile remained a fascinating demonstration, a temple wonder, never harnessed to pump water from mines or to drive the wheels of industry. Historians have long pondered why. Was it a lack of need, with abundant slave labor making such machines seem unnecessary curiosities? Or was it a failure of imagination, an inability to see this spinning sphere as anything more than a philosophical proof? The haunting question remains, if that single conceptual leap had been made, if the power of steam had been put to practical work, the course of our entire history might have shifted. The Industrial Revolution could have dawned in the 1st century, not the 18th, forever altering the rhythm of human progress. This small, spinning sphere represents one of history's most profound roads not taken. The Antikythera Mechanism was not an isolated miracle of engineering. It appears to have been part of a wider tradition of building mechanical minds in the ancient world. Archimedes himself, the legendary mathematician, was said to have constructed a portable planetarium, a self-contained model of the heavens that could be carried from place to place to demonstrate the intricate dance of the stars and planets. Another philosopher named Posidonius built a similar device called an orrery, which meticulously tracked the sun, the moon, and the 5 wandering planets visible to the naked eye. These were not simple decorative models. They were sophisticated analog computers used by astronomers and thinkers as both powerful teaching aids and precise calculation tools. The most brilliant aspect of their design was the use of differential gearing, a complex arrangement of interlocking gears that allowed the machines to account for the irregular speeds of celestial bodies. A planet does not move at a constant pace across the sky. It appears to speed up and slow down in its orbit. These ancient Greek devices could physically simulate that very irregularity through the precise mathematics of their gear trains. This technology was so advanced that it would not be reinvented in Europe until the 16th century, a gap of over 1,600 years. The existence of multiple such machines points toward a forgotten school of mechanical philosophy, a pathway where knowledge was encoded not just in scrolls, but in spinning bronze and turning axles. This entire branch of technological progress, this world of whirring celestial calculators, was then lost to the silence of the Middle Ages. We are left to wonder what other complex wonders were described in the scrolls of the Great Library of Alexandria, and what our world might look like today if that tradition of mechanical computation had never been interrupted. From the whirring gears of Greek calculation to the imperial courts of ancient China, another invention pushed the boundaries of what was thought possible. In the year 132, the brilliant court astronomer Zhang Heng unveiled a device of both artistic beauty and profound scientific purpose, the world's first seismoscope. Imagine a large, ornate bronze urn circled by 8 dragon heads, each one holding a single bronze ball in its jaws. Below each dragon, a corresponding bronze frog sat with its mouth open, waiting. According to historical records from the Han Dynasty, when an earthquake occurred even hundreds of miles away, the mechanism inside the vessel would react. One of the dragons would release its ball, which would clatter into the mouth of the frog below, clearly indicating the compass direction of the distant tremor. The internal workings remain a matter of scholarly debate, but the most accepted theory suggests a masterfully simple principle. A heavy, inverted pendulum was suspended in the center of the urn. When the faint but specific vibrations of a far-off quake traveled through the ground, the pendulum would sway, striking a lever mechanism that opened the jaw of just one dragon, the one pointing toward the quake's origin. The precision was staggering. The historical texts recount one specific instance where the dragon facing west dropped its ball, yet no one in the capital had felt a thing. Skeptical court officials wondered if the device had simply malfunctioned. Several days later, a messenger arrived from a western province, reporting a major earthquake that had struck at the exact moment the dragon had spoken. The epicenter was over 400 miles away. This was not a legend, it was a documented early warning system. Modern engineers have built functional replicas based on this inverted pendulum design, confirming that the basic principle is entirely sound. The device did not measure the strength of a quake, but it could sense the direction of the primary seismic waves, which travel faster and arrive before the more destructive shaking. Zhang Heng's seismoscope demonstrates a conceptual leap, an understanding that the Earth itself transmits signals we can interpret. It stands as a powerful testament to an ancient science that sought not just to explain the heavens, but to listen to the very ground beneath our feet. The same mind that mastered mechanics with celestial gearwork also turned its genius toward the defense of a city. As the Roman fleet closed in on Syracuse in the year 212 before the Common Era, a new and terrifying weapon was said to have been deployed from the walls. Soldiers, under the direction of Archimedes, raised a battery of highly polished bronze shields, angling them to capture the Mediterranean sun. They focused the reflected light onto the wooden hulls of the distant warships. Ancient historians like Lucian and Galen recount that a single, intense point of heat blossomed on the ship's timbers, smoke began to curl, and then, against all expectation, flames erupted across the tar-coated hulls. The Roman invasion force was reportedly set ablaze by nothing more than concentrated sunlight. For centuries, this account of Archimedes' heat ray was dismissed as pure legend, a fanciful story born from the great inventor's formidable reputation. The sheer scale and coordination required seemed implausible. Yet, modern scientific inquiry has reopened the case. A team from the Massachusetts Institute of Technology put the concept to the test. Using 127 large, polished bronze mirrors arranged in a precise parabolic formation, they focused sunlight onto a stationary wooden fishing boat. Within minutes, the target area charred and then definitively burst into flame. The experiment proved the concept was not just theoretically sound, but practically achievable. Whether the event occurred exactly as described is less important than the profound knowledge it represents. The ancient Greeks clearly understood the optical principles of reflection and focal points. They grasped that light could be concentrated and transformed into a different form of energy, heat of such intensity it could ignite objects at a distance. This legendary weapon directly anticipates the core technology behind our modern solar thermal power plants. Vast fields of mirrors, called heliostats, focus sunlight onto a central tower, generating immense heat to drive turbines and create electricity. A 2,000-year-old story of military ingenuity thus finds its echo in our contemporary quest for clean, renewable energy, a brilliant flash from the past that illuminates a path to the future. Buried within the ruins of a royal palace in Nimrud lay a small, unassuming piece of rock crystal. Unearthed by archaeologists in the mid-19th century, this object, dated to around 750 years before the Common Era, was no ordinary decorative stone. It was a carefully ground lens. The Assyrian craftsman who created it shaped the crystal into a slightly oval form with one flat and one convex side, a design that gave it a focal length of about 11 centimeters. In practical terms, it could magnify an object up to 3 times its normal size, or it could concentrate the harsh Mesopotamian sun into a pinpoint of intense heat. Its true purpose remains beautifully ambiguous. Was it a magnifying glass used by a skilled artisan to inspect intricate carvings or to set a fire with a focused beam of light? Some have even proposed it could have been part of a simple telescope, a tool to aid an ancient astronomer in mapping the heavens. While we may never know its exact application, the Nimrud lens is undeniable proof of a sophisticated understanding of optics. The skill required to grind and polish rock crystal to such a precise curvature is immense, speaking to a highly developed lapidary tradition. This single artifact predates the widespread use of corrective lenses in medieval Europe by over 1,600 years. Its existence forces a profound question. If one such lens survived, how many others were made and subsequently lost? Could this have been a lone experiment, or was it part of a broader, but now completely vanished, exploration of visual aids? This small piece of crystal is a silent witness to a path of optical science that was discovered, utilized, and then forgotten, waiting centuries for others to rediscover the principles it so elegantly embodies. That small crystal lens reveals an ancient curiosity with light, but a far larger and more durable object in India demonstrates a mastery over metal itself. Rising over 7 meters tall in Delhi, a solid iron pillar has stood completely exposed to the harsh elements for more than 1,600 years. It was forged during the glorious Gupta Empire around the year 400 of the Common Era, and it carries an inscription that is still perfectly legible today. The truly astonishing fact is not its age, but its pristine surface. While modern iron structures rust and crumble in a matter of decades, this ancient monument shows almost no sign of corrosion. It has withstood over 16 centuries of monsoon rains, scorching heat, and urban pollution, yet its surface remains smooth and remarkably intact. How did ancient metalworkers accomplish this feat of near-permanent preservation? Modern scientific analysis has uncovered the pillar's secret. The iron itself possesses a unique chemical signature, an unusually high amount of phosphorus, and a very low amount of sulfur. This specific recipe was not an accidental impurity. It was the direct result of a sophisticated and deliberate smelting process. The iron ore was processed using a special high phosphorus charcoal as fuel. As the metal was worked and hammered by skilled artisans, the phosphorus from the charcoal became integrated into the iron's very structure. Over time, this unique alloy, reacting with the relatively dry air of Delhi, formed an incredibly thin, invisible protective film on its surface. This layer, a compound called mesawite, acts as a perfect shield. It prevents oxygen and moisture from penetrating the metal beneath, effectively putting a stop to the corrosive process before it can truly begin. This is a phenomenon known as passive protection, the very same principle that underpins our modern stainless steel, an invention that would not emerge in the West until the 20th century. The ancient Indian ironsmiths had no knowledge of molecular chemistry, yet through generations of empirical experimentation, they perfected a formula that we would only rediscover millennia later. This pillar is not merely a monument to a king, it is a testament to a forgotten school of advanced materials science. Today, metallurgists study this ancient iron, hoping its secrets can lead to the development of new, more effective anti-corrosion technologies for our own world. It stands as a quiet, towering challenge to our assumptions about progress, proving that some of the most durable solutions were forged not in a modern laboratory, but in the fires of a 1600-year-old furnace. The same mastery over metal that created the rust-proof pillar of Delhi finds a stunning parallel in the ancient Persian mastery of a more elusive element, ice. In the heart of the desert, where summer temperatures could be searing, people enjoyed chilled delicacies and preserved food with ice harvested during the winter. This was not a luxury imported from distant mountains, but a resource created and stored locally through brilliant, passive engineering. The key was the yakchul, meaning ice pit, a structure that functioned as a massive, natural refrigerator. These domed buildings began appearing around 400 years before the Common Era, and their design was a marvel of thermal logic. They were not simple ice houses, but sophisticated climate control systems built from mud brick and a special water-resistant mortar called saruj. This unique plaster, made from sand, clay, egg whites, lime, and goat hair, provided exceptional insulation, resisting the transfer of heat from the scorching outside air. The most striking feature was the tall, conical dome, which wasn't just for appearance. Its shape allowed the hottest air inside to naturally rise and escape through openings at the very top, while the massive, deep underground storage chamber remained significantly cooler. But how did they actually make ice in a climate where nights might only be cool, not freezing? The process was a clever application of physics. Shallow, shaded canals were filled with water in the evening. Under the clear desert sky, this water would lose its heat through a process we now call radiative cooling, releasing thermal energy directly into the atmosphere. Even if the air temperature was a few degrees above freezing, the water itself could radiate away enough energy to form a thin layer of ice by dawn. Workers would then harvest this ice and pack it deep into the yakchul's insulated chamber, often layered with straw for extra protection. To enhance the cooling, many structures featured wind catchers, tall towers designed to catch any prevailing breeze and funnel it down into the storage space, creating a constant evaporative cooling effect. The result was a year-round supply of ice in the middle of an arid landscape. Some of these structures were so effective they could preserve ice through the entire summer and into the following winter. This was not magic, it was applied environmental science. The principles at work, using thermal mass, radiative cooling, and evaporative techniques, are the very same concepts that modern architects are now reviving to create sustainable, low-energy buildings. The Yakchul stands as a monument to a civilization that did not fight its environment, but instead learned to listen to its rhythms and harness its quiet laws to create comfort from the desert's harshness. The same empirical genius that forged rust-proof iron and cooled desert air was applied with startling precision to the most delicate of tasks, the human body. Within the leather rolls of a Roman surgeon's toolkit lay an array of instruments that feel unnervingly familiar. Fine bronze and iron scalpels with replaceable steel blades, intricate bone drills, and various specialized forceps for extracting arrowheads or holding tissues gently but firmly. Archaeologists have uncovered vaginal and rectal speculums with clever screw mechanisms that allowed for careful internal examination. There were even early syringe-like devices called clysters, used for irrigation or the application of medicaments. This was not a crude collection of generalized tools. Each instrument was purpose-built for a specific and often complex procedure. Delicate probes and hooks were designed for eye surgery, including the removal of cataracts. Trophines, which are circular blades, were used for a procedure known as trepanation, creating small openings in the skull, perhaps to relieve pressure from head injuries. The sophistication went beyond mere design and into a profound understanding of post-operative care. Roman medical texts, such as those written by the physician Aulus Cornelius Celsus, provide clear instructions that instruments should be cleaned and boiled before use. This recognition of sterilization, of the need to prevent infection from one patient to another, was a principle of hygiene that would not become standard medical practice again until the work of Joseph Lister in the 19th century. These tools reveal a medical culture that blended practical skill with systematic knowledge, capable of interventions that required remarkable steadiness of hand and clarity of thought. Yet this entire school of advanced surgical practice, with its specialized instruments and its principles of cleanliness, largely faded from common use during the following centuries. The knowledge was preserved only in a handful of manuscripts, waiting to be rediscovered during the Renaissance when European surgeons looked back to the ancient texts and found, to their astonishment, that they were not inventing modern medicine, but in many ways they were relearning it. The relentless power of a river could be channeled for more than just irrigation. Deep in the Roman province of Gaul, the ruins of the Barbagal Mill complex reveal an industrial vision that feels centuries ahead of its time. Built in the late 3rd century, this was not a single mill but a cascading powerhouse of 16 individual water wheels, arranged in 2 parallel rows down a steep hillside. An aqueduct delivered a constant stream of water to the top of the system, where it was directed to turn the first massive wheel. The used water then flowed down to power the next wheel, and then the next, creating a breathtakingly efficient cascade of energy. This was the ancient world's closest equivalent to a factory, a fully automated production line operating on a truly industrial scale. Historians estimate the complex could grind enough flour every single day to supply bread for the entire population of the nearby city of Arles, a community of over 10,000 people. The concept itself was even older. Centuries before Barbagal, the Greek engineer Philo of Byzantium had written detailed descriptions of water-powered mills, and archaeological evidence confirms their widespread use across the Roman world by the 1st century before the Common Era. But these were not just simple paddles turning in a stream. The true genius lay in the hidden gears, the Romans perfected systems of interlocking wooden gears that transferred the raw, rotational force of the water wheel to the heavy millstones above. These gear trains could be designed to adjust the speed and torque, allowing a fast-moving but weak water current to be converted into the slow, powerful grinding motion needed to crush grain. This fundamental principle of mechanical power transmission is the very bedrock of every machine that followed, from the textile mills of the Industrial Revolution to the gearboxes in modern automobiles. The existence of barbagal forces a profound reconsideration of the ancient economy. This was not a society reliant solely on human or animal muscle. They had grasped the potential of automation, of harnessing a natural, renewable force to perform work on a massive, continuous scale. The silence that fell over this complex and the long centuries that passed before such centralized industrial power re-emerged stands as one of history's most puzzling interruptions. What might have happened if this path of water-powered automation had continued to evolve, spreading to other forms of manufacturing? The whirring gears of barbagal were a whisper of a future that the ancient world glimpsed but ultimately left behind. While Roman water mills automated the grinding of grain, another civilization was perfecting a machine that automated the very concept of direction. Deep within the archives of ancient China lies the record of a legendary vehicle, the south-pointing chariot. First documented around the 3rd century of the Common Era, this was not merely a carriage, but a mechanical marvel of unparalleled ingenuity. Imagine an ornate chariot carrying a statue of a court official, his arm perpetually outstretched, pointing unerringly toward the south. No matter how many turns the chariot made, whether navigating a winding mountain path or a complex ceremonial procession, the figure on top never lost its bearings. Its extended finger remained a constant guide to the southern direction. This was not magic, nor was it a magnetic compass. It was a purely mechanical computer, an intricate clockwork mind built from interlocking gears. The secret lay in a brilliant system of differential gearing. As the chariot's wheels turned, they drove a complex assembly of gears inside the vehicle. The true genius of the design was its ability to automatically compensate for every turn. When the chariot turned left, the gears would subtract that rotational movement from the pointer. When it turned right, they would add it. Through this constant automatic calculation, the net rotation of the pointer remained zero, forever locked onto its southern heading. This means the device was not sensing the Earth's magnetic field. It was mathematically dead, reckoning its position based solely on the distance traveled and the angles of its turns. It was, in essence, performing integral calculus with wood and bronze. The engineering challenge was staggering. The gear train had to be perfectly calibrated to the circumference of the wheels, and the mechanism had to be robust enough to maintain accuracy over bumpy, uneven ground without slipping or jamming. Historical accounts suggest these chariots were used for important state ceremonies and by military commanders to maintain orientation during long campaigns through featureless terrain. The conceptual leap here is breathtaking. This mechanical computer demonstrated a fundamental understanding of feedback control systems, a principle that would not be formally developed in the West until the 19th century. The south-pointing chariot is a direct mechanical ancestor of the inertial guidance systems that navigate modern aircraft and spacecraft today. Those systems also track every movement to calculate position without any external reference, just as the ancient Chinese chariot did. Its existence poses a haunting question. How far could this path of mechanical computation have gone if it had been pursued with the same fervor as our digital technologies? It stands as a monument to a road of technological development that was fully realized, then quietly set aside, a ghost of a different possible future for automation. A spiral turning inside a hollow tube seems almost too simple to be revolutionary, yet this elegant concept, known as Archimedes' screw, became one of the ancient world's most enduring mechanical gifts. Attributed to the genius of Archimedes in the 3rd century before the Common Era, its purpose was brilliantly straightforward: to lift water from a lower level to a higher one. As the spiral helix rotates inside its cylindrical casing, water is scooped up into the bottom pockets of the screw. With each turn, these captured pockets of water are gently carried up the incline until they tip out at the top, delivering a continuous, reliable flow. The device possessed a quiet perfection. It needed no complex valves that could clog or break. It could effortlessly handle water thick with silt, sand, and organic debris that would instantly jam a more intricate pump. And its robust design meant it could operate for years with almost no maintenance, powered by nothing more than human labor or a turning animal. This simple screw transformed the ancient landscape. Farmers used it to raise life-giving water from rivers to irrigate their fields, turning arid land productive. Miners deployed banks of these screws, working in succession, to drain floodwaters from deep underground tunnels, allowing them to reach previously inaccessible mineral wealth. On the vast trading ships of the Mediterranean, smaller versions tirelessly pumped water from the bilge, keeping vessels afloat and secure. The true testament to its design is that it has never really been replaced. You can find modern, electrically powered Archimedes screws at work today in municipal wastewater treatment plants, where their gentle handling and ability to move slurry without clogging are invaluable. They are used in large-scale agricultural projects and have even been ingeniously adapted into fish-friendly pumps, allowing salmon to migrate upstream through special channels built into dams. The screw's enduring success lies in its masterful application of first principles. It harnesses fundamental physics, the inclined plane, and the movement of fluids within a confined space, with such optimal efficiency that 2,000 years of technological progress have found little to improve upon its core design. It stands as a quiet, humming monument to the idea that the most advanced solution is not always the most complex one, but rather the one that solves the problem so perfectly it becomes timeless. The same ingenuity that lifted water from rivers and ground grain with water wheels also mastered the comfort of the indoor world. In the heart of a Roman villa during a frigid winter, the stone floors were not cold to the touch but pleasantly, evenly warm. This was the gift of the hypocaust, the world's first central heating system. While famously adopted and detailed by the Roman architect Vitruvius, the core technology was likely a Greek innovation, perfected for the sprawling bathhouses and luxurious homes of the Roman world. The principle was one of beautiful simplicity and profound understanding. The floor of a room was raised on countless short pillars of brick or stone, creating a hidden, hollow space beneath. A constantly burning furnace, stoked by servants in an adjacent room, would send hot air and gases flowing into this cavern. The heat would then slowly rise, warming the solid marble or tile floor above from below before being drawn up through carefully placed hollow tubes inside the walls, finally escaping through chimneys in the roof. This created a constant, gentle circulation of warmth. In the most advanced installations, ceramic box tiles were actually built into the walls themselves, turning entire rooms into massive radiators that emitted a soft, pervasive heat. This was not a mere fire in a hearth. It was a building designed as an integrated heating appliance. The knowledge of thermodynamics and airflow required to engineer such a system was remarkable. The builders had to understand how to create an even draw, how to size the flues to ensure the hot gases circulated fully without backing up, and how to use thermal mass in the floors and walls to store heat and release it slowly over time. This elegant solution transformed daily life, allowing for communal bathing in vast, warm halls and comfortable living spaces, even in the chilliest provinces of the empire. Then, this knowledge faded. The hypocaust's principles of radiant heating would not be widely rediscovered in Europe until the 19th century, a gap of over 1,000 years. Today, the technology finds its direct descendant in our modern radiant floor heating systems, where pipes of hot water or electric coils achieve the same goal of even, efficient warmth. The hypocaust stands as a powerful reminder that ancient innovation was not only about grand machines, but also about the quiet, sophisticated science of everyday well-being. A crusader knight testing his own sturdy blade against a captured Islamic sword would have witnessed something that defied all his understanding of steel. His own weapon might chip or bend, while the curved blade of his opponent, with its flowing, watery pattern on the surface, could slice cleanly through his armor and still retain its lethal edge. These were the legendary swords of Damascus, forged from a special type of high-carbon steel ingot known as woots, which originated in India. The magic was not in the raw material alone, but in a transformative, closely guarded manufacturing process that elevated metalworking to an art form of almost mythical precision. The smiths would heat the woot steel to a very specific temperature, not so hot that it became molten, but just hot enough to be workable. They then hammered and folded it with an exacting rhythm, controlling the cooling process over many days. This intricate dance of heat and force coaxed microscopic structures to form within the metal itself. For centuries, the source of the blade's power was a complete mystery, its secret dying with the last master smiths by the 18th century. It was only with the advent of modern electron microscopes that we could finally peer into the soul of this ancient steel. The stunning revelation was that the rippling patterns were not merely decorative. They were the visible signature of an incredibly advanced internal architecture. The steel contained carbon nanotubes, tubes of carbon atoms arranged in a hexagonal pattern, alongside incredibly hard nanowires of a substance called cementite. These nanostructures acted as a microscopic reinforcement, a built-in skeleton that gave the blade its legendary properties. They prevented the spread of cracks, granted incredible flexibility and toughness, and even created a self-sharpening effect. As the blade was used, the softer steel around these ultra-hard nanowires would wear away slightly, constantly exposing a fresh, razor-sharp edge at the microscopic level. This means that centuries before the term nanotechnology was ever coined, empirical craftsmen in Damascus and beyond were deliberately engineering materials at the molecular level. They had no knowledge of atoms or nanotubes, yet through generations of painstaking experimentation, they developed a repeatable process to create them. Modern metallurgists, with all their advanced tools and scientific understanding, are still trying to reverse engineer and perfectly replicate the exact conditions that produced this legendary steel. The loss of this technique stands as one of history's most poignant reminders that the pinnacle of human achievement can be as fragile as the knowledge required to sustain it. A bronze bird could sing, its melody powered not by breath, but by the precise hiss of steam and the turn of a gear. In the workshops of ancient Greek engineers like Heron of Alexandria, the line between machine and life was deliberately blurred. They built automata, self-operating devices designed to astonish and serve. Picture a small theater where no human actor treads the stage. Heron designed one such marvel, a programmable play that unfolded entirely on its own. The performance began with the creak of a hidden mechanism, a system of ropes meticulously wound around a rotating axle, slowly unwound over the course of the show. This single turning cylinder acted as the program, its carefully placed pegs and levers triggering a sequence of events. Wooden set pieces would glide into place on their own. Small figures of actors moved across the stage, performing a simple myth. Sound effects of thunder would rumble from a hidden chamber where metal balls were dropped onto a sheet of brass. It was a mechanical ballet, a preordained sequence of actions driven by a simple yet brilliant programmable controller. This was not the only wonder. In temples, worshippers might witness a miracle as doors swung open seemingly by an invisible hand when a fire was lit upon the altar. The mechanism was a masterclass in energy conversion, using the expansion of heated air to displace water, which then turned weights and pulleys to move the heavy doors. These inventions were far more than clever toys. They represent a foundational understanding of automation and sequential control. The automated theater was running a physical program, its sequence of actions determined by the arrangement of pegs on a drum, a concept that directly anticipates the punch cards used to program early computers. The engineers of this era had grasped the core principles of robotics, feedback, and programmed movement. They created machines that could perform complex, multi-step tasks without human intervention once set in motion. Yet this entire branch of technology, this path toward a world of mechanical servants and automated entertainment, faded into obscurity. The knowledge was preserved in a handful of manuscripts, but the practical art was lost. For nearly 2 millennia, the world would lack such sophisticated automata until the clockwork geniuses of the 18th century began to reinvent them, unaware that they were walking a path first laid out in antiquity. How different might our world be if this tradition of programmable machines had continued to evolve without interruption? The same mastery that heated homes and forged legendary steel also shaped the very landscape to bring life itself, water, across impossible distances. To walk the path of a Roman aqueduct is to witness a monument not of stone, but of sheer will, a channel of water flowing for dozens of miles with a slope so gentle it is almost imperceptible. Engineers achieved gradients as slight as 1 inch of drop for every 250 feet of channel, a precision that seems to defy the ruggedness of the ancient world. This was not guesswork, it was the result of advanced surveying tools like the chorobates, a long, precise leveling instrument that used water channels to establish a true horizontal over vast stretches of countryside. The entire system operated on a single, elegant principle, gravity. From a mountain spring to a city's heart, the water flowed entirely downhill, a self-sustaining river guided by human genius. But the journey was far from simple. When an aqueduct met a deep valley, Roman engineers did not always build a towering arch bridge. Instead, they often employed an inverted siphon. This involved channeling the water into sealed lead pipes that ran down one side of the valley, across the bottom, and then back up the other side. The physics here are profound. The water, forced down under immense pressure, would then rush up the far side, pushed by the weight of the entire column of water behind it, often reaching nearly the same height from which it started. To withstand these incredible forces, the pipes had to be incredibly strong, and the Romans used thick lead sleeves and massive stone supports to anchor them. Before this water ever reached a city, it was cleansed. Settling tanks were built at regular intervals along the route. Here, the water would slow down, allowing sand, silt, and other impurities to gently settle to the bottom, leaving a clearer flow to continue its journey. Upon arriving at the city's edge, the water entered a massive distribution tank called a castellum aquae. This was the system's beating heart. From this central reservoir, a network of calibrated bronze pipes directed the flow to public fountains, lavish bathhouses, and the private homes of the wealthy. The engineers even understood how to manage water pressure using different pipe sizes and vents to prevent destructive surges. The scale of this achievement is almost incomprehensible. The aqueducts serving the city of Rome itself delivered over 300 million gallons of water every single day, a supply per person that rivals what many modern cities provide. This was not merely a convenience, it was the foundation of urban life, enabling public health, sanitation, and social grandeur on a scale that would vanish for over 1,000 years after the empire's decline. The silent, steady flow of these ancient channels represents a pinnacle of civil engineering, a systematic approach to public utility that directly anticipates the very water management systems we rely on today. What does it mean that a 2,000-year-old infrastructure project still stands as a benchmark for how we nourish our own modern cities? The meticulous observation of tremors in China extended far beyond a single brilliant device. For centuries after Zhang Heng, imperial scholars maintained a continuous, disciplined record of the Earth's restlessness. They created the world's first systematic seismic catalogue, a sprawling archive that transformed random events into a body of data ripe for analysis. These court astronomers did not merely note that an earthquake had occurred. They documented the precise time, the direction of the shock, its perceived intensity, and any peculiar phenomena witnessed in its wake. By the 9th century, this deep well of recorded knowledge had yielded profound insights. Chinese texts began to describe the identification of specific seismic zones, regions recognized as being particularly prone to tremors. They even recorded patterns of foreshocks, the smaller tremors that sometimes precede a major event, demonstrating an early understanding of earthquake precursors. One of their most staggering innovations was the development of isosysmal maps. These were diagrams that used contour lines to connect all the points that experienced an equal level of shaking during a particular quake. This technique, which visually represented the distribution of seismic force across the landscape, would not be formally developed in Europe until the 19th century. The Chinese approach was remarkably holistic. Scholars carefully noted correlations they observed between seismic activity and other natural cycles. They tracked potential links to lunar phases, recorded unusual atmospheric phenomena like strange cloud formations or unexpected weather, and documented accounts of unusual animal behavior preceding major tremors. This was not superstition, it was a rigorous empirical methodology. They were gathering all available data, searching for patterns in nature's complex web. This centuries-long project of observation and classification represents a scientific mindset that feels strikingly modern. It was a system built not on abstract theory, but on the patient accumulation of evidence. The goal was practical, to understand these destructive events well enough to potentially anticipate them and mitigate their impact on society. This entire school of thought, this empirical pathway to understanding the planet's dynamics, represented a branch of science that would not become standard practice in the West for many more centuries. The silent work of those ancient scribes, diligently noting every tremor and its effects, laid the foundational principles of the seismology we rely on today, proving that the most powerful tool for understanding the Earth is often simply the will to watch, to record, and to learn. That same mastery of light and guidance found its ultimate expression in a tower that became one of the 7 wonders of the ancient world. The lighthouse of Alexandria did not merely warn ships, it was a colossal instrument of optical engineering. For nearly 1,500 years, its flame was a constant beacon on the Egyptian coast, a feat of endurance that no modern structure can yet claim. Rising over 100 meters, its white marble facade was visible from staggering distances, but its true genius was hidden at the summit. Ancient historians describe a massive, polished bronze mirror, a parabolic dish of immense scale. During the day, this mirror would capture the Mediterranean sun, focusing its rays into a brilliant, directional beam that could be seen dozens of miles out to sea. At night, the same mirror would reflect and project the light from a great furnace, magnifying a simple fire into a guiding star for mariners. The stories of this mirror being used as a weapon to set enemy ships ablaze are likely more legend than fact, a testament to the awe it inspired. Yet the underlying principle was sound. The architects clearly understood how to shape reflective surfaces to control and project light with incredible precision. This was not a simple bonfire on a hill, it was a calibrated optical system. The entire structure was a marvel of resilience, surviving for centuries through a combination of brilliant foundation work and its sheer, robust mass. Its eventual loss to a series of earthquakes was a catastrophe for seafaring knowledge. The design principles it established, of a tall, stable tower with a focused, amplified light source, became the blueprint for every lighthouse that followed. This ancient wonder directly anticipated the Fresnel lenses and powerful lamps of modern lighthouses, proving that the fundamental solution for safe navigation was discovered not in the age of steam, but in the age of bronze and marble. It stands as a silent, lost giant whose light, both literal and intellectual, guided the world for longer than most civilizations have endured. A quiet revolution in medicine was unfolding along the banks of the Ganges River centuries before Hippocrates. The Sushruta Samhita, a comprehensive medical text compiled around 600 years before the Common Era, documents a surgical tradition of breathtaking scope and precision. This was not a collection of folk remedies, but a systematic science. Its pages detail over 1,100 different diseases and describe the use of more than 700 medicinal plants. But its true genius lay in its approach to the human body itself. Ancient Indian physicians, led by the legendary surgeon Sushruta, performed incredibly complex operations. They developed a detailed procedure for removing cataracts, using a specialized, curved needle to gently displace the clouded lens and restore vision. They understood how to safely perform cesarean sections and even documented early forms of brain surgery. Their anatomical knowledge was profound, with meticulous descriptions of muscles, joints, and bones that demonstrated a deep familiarity with the inner workings of the human form. The tools they devised were equally sophisticated. Archaeologists have uncovered evidence of over 125 distinct surgical instruments from this period, each designed for a specific purpose. There were scalpels of various shapes for different incisions, probes, forceps, and specialized needles for suturing. What is perhaps most startling is their clear understanding of principles we consider modern. The texts explicitly stress the critical importance of sterilization, instructing surgeons to fumigate the operating theater with herbal vapors and to clean their instruments with hot water and specific plant-based antiseptics. They understood wound management, describing how to drain infections and promote clean healing. The Sushruta Samhita even outlines the ideal conditions for an operation, emphasizing proper lighting, correct patient positioning, and the precise handling of instruments, creating a standard of care that feels remarkably contemporary. Their most enduring legacy might be in the field of reconstruction. These ancient surgeons perfected techniques for rhinoplasty, the reconstruction of a nose. This procedure often involved cutting a flap of skin from the patient's cheek or forehead and carefully grafting it into place to form a new nasal structure, a complex plastic surgery that would not be formally reinvented in Europe until the Italian Renaissance more than 2,000 years later. This entire medical system represents a parallel evolution of scientific thought, a school of medicine that independently arrived at principles of hygiene, anatomy, and surgical intervention that would become the bedrock of modern practice. Its existence challenges the linear narrative of progress, revealing that the quest to heal the human body achieved stunning heights in multiple corners of the ancient world, only for some of its most advanced knowledge to fade into history, waiting to be rediscovered. The crown jewel of Roman concrete engineering remains the Pantheon, a structure that has defied gravity and time for nearly 2,000 years. Its magnificent dome is not merely large, it still holds the title of the world's largest unreinforced concrete dome, a record unchallenged by 2 millennia of architectural progress. To achieve this, Roman builders employed a suite of revolutionary techniques that speak to a profound, intuitive understanding of structural physics. They engineered the very fabric of the dome itself, using different concrete formulas at different heights. At the heavy, supporting base, the concrete was dense and strong, mixed with heavy travertine stone. But as the dome soared upward, the mixture was deliberately lightened. Engineers incorporated lighter volcanic materials like pumice and tufa into the upper layers, meticulously reducing the overall weight and the immense downward thrust on the supporting walls. This was not a single monolithic pour, but a carefully calculated gradient of material strength and weight, an ancient form of smart design. Further genius is etched across the dome's interior surface. The famous coffered ceilings, those elegant, sunken square panels, are not just decorative. Each indentation carves away non-essential mass, lightening the load without compromising the dome's structural integrity. At the very apex, the central oculus or opening serves a dual purpose. It bathes the vast interior in a shifting column of natural light, but it also acts as a brilliant stress reliever. This open eye at the top eliminates what would be the heaviest and most unstable point of the entire structure, the center of the crown. The dome's design is a masterclass in compression, its entire shape perfectly configured to channel its immense weight downwards and outwards into the thick cylindrical drum that supports it. Perhaps the most staggering feat was its construction. Roman engineers built enormous wooden centering, a temporary support structure of breathtaking scale, to hold the wet concrete in place until it cured and could support itself. The Pantheon stands as a silent lesson in architectural harmony, where form, function, and material science merge to create a space of unprecedented scale. Its principles of weight distribution, material gradation, and compression management are concepts that modern architects and engineers continue to study, a testament to a peak of ancient innovation that anticipated the very goals of our own large-span structures. While Roman concrete shaped cities and Greek automata dazzled the senses, an industrial revolution was quietly unfolding in ancient China, powered by an invisible force. Deep beneath the earth, engineers discovered how to harness the energy of natural gas, creating the world's first fossil fuel industry over 2,000 years ago. They sought not gold or jewels, but a far more vital resource, salt. To produce it on a massive scale, they developed a system of breathtaking complexity. Using bamboo towers and heavy iron drill bits, they bored deep into the earth, sometimes reaching astonishing depths of over 1,000 meters. They achieved this with a clever percussion drilling technique, raising and dropping a heavy iron bit suspended by incredibly strong bamboo cables, slowly punching through rock layer after layer. Once they struck gas, the challenge became one of control and transport. They engineered vast networks of bamboo pipelines, sealing the joints with clay and lacquer to create airtight conduits that could carry the volatile gas for miles across the countryside. This gas was then channeled to vast salt works, where it fueled roaring fires under massive iron pans, boiling brine until only precious salt crystals remained. This was not a small-scale operation. It was a highly organized industrial process that supplied an entire civilization. The engineers even incorporated sophisticated safety measures, using a kind of primitive cement to seal their boreholes and designing valve-like systems to regulate the dangerous flow of gas. This entire operation, from deep earth extraction to long-distance distribution, represents a monumental leap in applied energy science. It means that while much of the world relied on wood or charcoal, ancient China had already unlocked the potential of subterranean fuel, creating a technology that would not be seen in the West for centuries. How many other such sophisticated energy systems have been lost to time? Their bamboo pipelines and derricks long since returned to the earth, leaving only the faintest echo of their industrial hum. 2,500 years ago, a philosophical debate was raging that would one day form the bedrock of modern physics. Greek thinkers Democritus and Leucippus challenged the prevailing view of matter, suggesting it was not infinitely divisible. They proposed that everything in existence was composed of unimaginably small, indestructible particles they named atomos, meaning uncuttable. These particles, they reasoned, moved and interacted in an endless void, their combinations and separations giving rise to the immense variety of substances we perceive. The hardness of iron, the fluidity of water, the warmth of a flame, all of it was merely the result of different atom shapes and configurations. This was a purely theoretical model, a brilliant leap of logic without any means of experimental proof. Yet the concepts they laid out are startlingly familiar. They described a universe governed by material interactions, not by the whims of capricious gods. This materialist framework was a radical departure, suggesting that nature followed consistent, knowable rules. The idea that physical properties emerged from the behavior of invisible particles is a core principle of modern chemistry and materials science. For over 2 millennia, this theory remained a fascinating footnote in philosophical texts, a ghost of a possibility. Its rediscovery during the Renaissance, as scholars eagerly translated ancient Greek works, provided a crucial intellectual spark. It gave pioneers like Newton and Boyle a conceptual foundation to build upon, a language for thinking about matter in a new way. The journey from the philosophical atomos of Democritus to the experimentally verified atom of John Dalton in the 19th century is one of the longest and most profound in the history of science. It shows us that the power of a single idea, even one born from pure reason, can echo through the centuries, waiting for the tools and the time to prove its truth. The brilliance of these ancient minds casts a long shadow, one that makes their sudden disappearance all the more perplexing. How could such profound knowledge simply vanish from the world for 1,000 years or more? The answer is not a single event, but a slow unraveling of the very fabric that holds technology together. Before the printing press, knowledge was a fragile thing, etched onto fragile scrolls or locked away in the minds of a few master craftsmen. A single fire, like the one that consumed the Library of Alexandria, could erase entire schools of thought in an instant. Specialized craft traditions were often family secrets, passed from parent to child in a delicate chain that could be broken by war, illness, or a simple lack of interest from the next generation. Political collapses were perhaps the most devastating. When empires like Rome or the Han Dynasty fragmented, the vast technological ecosystems they supported crumbled with them. The intricate trade networks that supplied rare materials, the state funding for massive projects like aqueducts, the peaceful conditions needed for experimentation, all of it could disappear in a generation. Many of these inventions were also victims of their own success. They were often luxury items for the elite or closely guarded military secrets, like Greek fire, never diffusing into the wider economy where they could spur further innovation. A society with abundant slave labor had little economic incentive to develop labor-saving machines on a grand scale. Why build a steam engine to pump water from a mine when you have countless human hands to do the work? This confluence of factors, from the interruption of trade routes during great migrations to shifting cultural priorities that valued philosophy over mechanics, led to periods of profound technological regression. Progress, it turns out, is not a steady upward climb. It is a fragile flame that can be dimmed for centuries, a story of brilliant flashes followed by long periods of forgetting. This historical pattern gives our own era a profound responsibility, a reminder that the knowledge we take for granted is not a permanent possession, but a legacy we must actively preserve and pass on. This journey through 25 forgotten inventions leaves us with a profound realization. The ancient world did not simply stumble upon isolated curiosities. It achieved a sustained level of scientific and technological sophistication that came breathtakingly close to our modern world, not just once, but across multiple disciplines. From the mechanical computation of the Antikythera device to the potential of Heron's steam turbine, from the rust-proof chemistry of the Delhi pillar to the systematic seismology of ancient China, we see a pattern of brilliant flashes illuminating the past. This legacy fundamentally challenges our linear view of progress as a steady, upward march. It reveals a far more complex story, one of peaks and valleys, where knowledge is not a permanent possession but a fragile flame that can be dimmed for centuries. The loss of these technologies forces us to confront a sobering truth. Human ingenuity has always burned brightly, but the conditions needed to sustain and transmit that brilliance across generations are remarkably delicate. The philosopher George Santayana offered a timeless warning that those who cannot remember the past are condemned to repeat it. In this context, his words carry a new weight. By studying these ancient innovations, we are not merely admiring museum pieces. We are learning from a vast, uncredited research and development phase of human history. We gain a deeper appreciation for the resilience of the human mind and the timeless quest to understand our world. But more than that, we gather valuable insights. The self-healing Roman concrete offers clues for more sustainable building materials. The mechanical principles of the south-pointing chariot inform modern guidance systems. The empirical mastery of Damascus steel inspires new frontiers in material science. Each forgotten invention is a lesson waiting to be relearned, a spark that could ignite a future breakthrough. Our own era of rapid advancement stands on the shoulders of both remembered and forgotten giants. The cycle of discovery continues, forever building upon the wisdom, both preserved and lost, of those who came before us. The final question these stories leave us with is not just what our ancestors knew, but what we ourselves might be on the verge of forgetting and what we will choose to pass on. These hidden threads of innovation woven through time invite us to become active participants in the story. If the spark of curiosity has been lit, then the journey does not end here. You can follow it into the world, researching the specific inventions that captivated you most, from the whirring gears of the Antikythera Mechanism to the silent endurance of the Delhi pillar. Consider how these ancient breakthroughs subtly influenced later technologies, creating a conversation across centuries that we are only now beginning to hear. We would love to know which forgotten marvel you find most remarkable. Share your thoughts in the comments and tell us which modern technology you suspect might have a parallel waiting to be discovered in the ancient world. For more explorations into the fascinating crossroads where history, science, and human ingenuity meet, be sure to subscribe to this channel. Turn on notifications so you can join our future investigations into humanity's vast and often surprising innovative heritage. The past is not a closed book, but a living library, and its pages still hold profound lessons about the resilience of creativity and the unexpected journeys of invention that continue to shape our lives in ways we are only just beginning